Okay, listen please. Now, continuing on to essentially Friday, where we will be ready for a test on next Tuesday. Listen up. Last couple of days, especially yesterday, I taught you a method in which we can draw Lewis structures, and those Lewis structures can have atoms that involve coordinate covalent bonds, which means some of the atoms might have extra bonds and it might not look as nice as we're used to. In actual fact, what I taught you yesterday is the normal way to draw a Lewis structure. In reality, there are more molecules that break the nice rules than there are nice molecules. There are actually only a few molecules that are nice and easy to draw where they always follow what we call the valence rule, right? We've got things like water, H2O, that follows it nicely as well. HCl also follows it very nicely, all of those simple little molecules. But in reality, there are more ions and molecules out there that don't follow the rule. So what I actually taught you yesterday is the way you draw Lewis diagrams, whether you get a nice one or not. Now, we're going to have, on our tests, I'm going to indicate to you whether it's nice or whether it's not, so that you still have that scaffolding to think about. Oh, okay, this is a nice one, I can just draw that out, or this one needs a little extra effort. But as you go on in chemistry, it'll be just, draw these Lewis diagrams if you need it, right? The Lewis diagram is actually a tool to help you learn a lot more about that particular molecule. And we're actually going to use that today. So now I'm going to check off that box. They have mastered drawing Lewis diagrams. Everybody did very good on that assignment. They must have mastered it. They wouldn't have copied their neighbors. That would just be wrong. So mastery, done. We will move on to the next thing so that, we can get to the end of the unit. And here's the next thing. What we want to talk about now is the bond itself. It doesn't matter whether we're talking about a single bond, double bond, or triple bond. In the examples I'm going to do, they're all going to be single bonds, but that's immaterial. What we want to talk about now again is that bond itself and the sharing involved in the bond. And as you can see here, we're going to be talking about a variation on the bonds called polar bonds, all right? Now, it's not a new type of bonding. It's still going to be single, double, triple, perhaps a coordinate covalent bond, but it's going to be describing how the sharing of electrons is taking place in that bond. So we're going to look very closely at the sharing of electrons. Before you write this slide down, let me just bring it up to a certain spot. Normally, I'm not a fan of animations and all that stuff, but I want to bring it to here. Don't write yet. Let me just talk. I'll bring the third box up, then you can write. At this point, you know of bonding as being either ionic, a complete transfer of an electron from a metal atom to a nonmetal atom. We did that way at the beginning, right? Put a sodium with a chloride. The electron gets transferred to the chloride. We draw up the Lewis diagram. Nice stuff. Or covalent bonding, equal sharing of a pair of electrons between nonmetals, right? Bring a couple of hydrogen atoms together. They form a single covalent bond, and we have sharing, right? Even though I've already indicated to you that it really isn't sharing. It's more of a tug of war. And that's what we really need to talk about today, because if I put two different atoms together, something like hydrogen and chlorine, then when they form a bond, it turns out that the sharing isn't equal at all. And I've already mentioned to you a term that we use to determine how unequal the sharing is. And that was at the very end of our last chapter, and that was a term called electronegativity. What a great word. It's got all those electricity and negativity and all that good stuff in it. And that was a number that determined how strong that atom pulled on electrons. Because if one atom pulls harder than the other, then we don't have equal sharing, but we don't have a complete transfer, but we have something in the middle, some kind of unequal sharing. And that's what we want to talk about today, the unequal sharing of electrons. And we call these middle-of-the-road type bonds we call them polar covalent bonds, unequal sharing. So now you can write that all down, if you can see it. Can you see it? All right, good. Now we need to recall, because I did show you this very briefly, but if you can't recall, it's not a big deal, how we are going to quantify this unequal sharing, all right? And the number we use is the electronegativity. So you're going to need your periodic tables, because you're going to need to find those little electronegativity numbers. You're going to need a calculator, because we're going to have to do some simple calculations, but not easy to do in your head. So a calculator is very handy. And essentially, the thing that we're going to be looking at are the electronegativities, but not just the electronegativity number, but the difference between them. We're going to be doing some subtraction today, exciting stuff. But we're going to be subtracting some decimals, so we're going to need to have the calculator. Again, you can write this down. This is all important information. I'll talk about it in a moment. Now that symbol there in brackets, that triangle, we read that as a delta, all right? It's a Greek letter, all right? It's the Greek letter D, and it's a capital delta. And in science, physics, math, it often means the change in or the difference in. So if you're taking physics with Mr. Petrus, you've probably done some delta D over delta T calculations, right? It means you just subtract the two numbers. How much is it different by? And that's the same here. In this case, we just want to know the difference in the electronegativities of the two elements that we're looking at. In the second bullet, it simply states, if the delta En, if the difference is large, that means that one atom is pulling much harder than the other atom. It means it's more ionic. It's getting closer to being a complete transfer. One of the atoms is stronger than the other and pulling those electrons closer. And if the delta En is very small, then it indicates more equal sharing, the electrons sitting in the middle. So it's not the electronegativity number itself, but it's the difference between the two atoms that are forming the bond that is going to determine how polar the bond is. So before we do some calculations, I'm going to show you a little table, and then we'll do some practice calculations right on there just to show you where different bits of information fit on this table. This table, though, as you'll... Oh, no. Ah. So let me bring the whole thing up. Again, I don't know why I have animations on it. Let me bring the whole thing here so that you can digest it. If we do a calculation between two atoms, and the difference in the electronegativity, the answer we get falls between 0 and 0.2, then we say that the sharing is practically equal. We say that it's a non-polar bond. if the difference in the electronegativity is between 0.2 and 1.7, chemists have decided that that mathematical value indicates that the sharing is unequal. It's not a complete transfer, but it's unequal sharing. And we call bonds in that region polar bonds. And if the difference in electronegativity is greater than 1.7, and you really don't have to worry about the maximum value there, it tops out because fluorine has an electronegativity of about 4, so it doesn't matter what the top number is. But if it's greater than 1.7, then we say that it's a complete transfer. It's ionic. Now this hopefully, eventually, will change your view of what an ionic bond is and what a covalent bond is. What we're trying to show you here is that it's not as cut and dry as you learned in grade 10 and what we've been talking about here. It's not simply a transfer, metal, nonmetal, and sharing two nonmetals. It has to do with that electronegativity of the two atoms. Notice it's called a continuum. That means it's not a discrete rule. It's not covalent and ionic, but it's a continuous transformation from equal sharing to not so equal sharing to so unequal we call it a transfer. Okay, another example of a continuum is a rainbow, all right? A continuous spectrum. We've already come across that in this class. It means we go through all the different colors of the rainbow without there being chunks in it. It's not a line spectrum, but it's a continuum, a gradual change. Same thing with bonding. Bonding can be kind of nonpolar, or it can be right on the edge of being polar, but yeah, nonpolar. It can be weakly polar. It can be in the middle of being polar. It can be strongly polar, and it can be so strongly polar it's ionic, depending on what the atoms are. So let's take a look at some examples. And I've put these examples on the chart in the position that I want to do them. So this is on the left because this is a nonpolar example. So you can write that down below the nonpolar region. And when we look at bonding, we need to draw a Lewis diagram so that we can see the bond we want to study. So let's draw a Lewis diagram here of H2, and I'm hoping that that's not a surprise to you. And now we're going to do a little calculation underneath. I'm going to do the delta En. And I'm really running out of room here on the left-hand side of my screen, but it's not too bad. Equals and I want absolute values there. Absolute values simply mean that I don't care about the sign. Don't worry about whether one's negative and one's positive. So what's the electronegativity of hydrogen? 2.2? 2.2 minus 2.2, and this one's easy. No calculator needed. I'll get this one for you guys. 0. It means that both atoms are pulling exactly equally in strength. So the electrons exist right in the middle of the bond, and we have perfect sharing. We actually have a special name for this one. This is a pure covalent bond. When identical atoms are bonded, it's pure, it's perfect, perfect sharing. Okay? Let's do another example. HCl. Again, let's draw a Lewis diagram of that. And I'm going to need the electrons. And these are nice ones. I'm hoping we've done enough of them. You can see, oh, one H with one Cl. Yeah, that's going to be nice. That makes good sense. Do the delta En. Delta En. 2.2. We've just used H, and I'll take Cl when you find it. We got a number? Yep. 3.16. 3.16. Notice if I did 2.2 minus 3.16 in my calculator, I'm going to get a negative number. The absolute value says, don't worry about the negative. We just want to know the size of that thing. I'm not doing that in my head. What do we get? 0.96. Notice the electronegativity, the difference in it, falls in the range of 0.2 to 1.7. This would be described as a polar covalent bond. It would be unequal sharing. Which atom would the pair of electrons be closest to in the bond between an H and a Cl? Which atom would the pair of electrons be closest to? Yep. Cl. Why? That's exactly correct. And it's closer to the right, it's got a higher electronegativity. That's the answer. If it has a higher electronegativity, it has a stronger pull, the electron resides closer to it. Now, we're not going to change the way we draw the bond, but in a moment I'll show you how we indicate that. All right? For now, let's move on to one more example, and then I'll come back to the polar covalent bond, because that's the one that we haven't seen yet. Let's do NaCl just to complete it. And I'm not going to draw the Lewis diagram yet, because many of us often make the mistake and draw it like a molecule, but this example is going to fall in the ionic region, so we actually should draw it like an ionic compound. First, let's do the calculation. I'm leaving some space here, so I'll do the delta En right here. You can do the delta En underneath with a little bit of room to draw a picture. I don't know what Na is, but Cl was 3.16. What is the electronegativity of sodium? Yeah, what do you got? 0.93, 0.93. Notice the trends that we've already learned. Metals, really low, right? Non-metals, really high. And the further to the right we get, the higher it gets. What do we have for a delta En? Somebody calculate that up. Yep. 2.23, 2.23. Which means this particular delta En falls within the ionic range. Which means if I'm going to draw a Lewis diagram, I should have that chlorine, which has gained the electron away, just like we did at the beginning of this unit, right? That has now become a chloride along with the sodium. That is now a plus sodium 1 ion. So I really shouldn't draw it with a bond because it's not bonded to it. It's an ionic compound. Okay? So here we've got equal sharing, not exciting whatsoever. Here we've got like the opposite of equal sharing, like the worst sharing ever. Big delta En, it means that the electron's been moved completely over to the Cl. What I want to do now is I want to come back and address the HCl. I'm going to draw another picture of the HCl. You can draw it below yours as well. Make it a little larger. HCl. I want to talk a little bit about why we call this a polar bond and how we indicate on the picture that it's polar. This bond, its charge movement exists somewhere between equal sharing and total unequal sharing, complete transfer. When we have a complete transfer, the chlorine becomes completely -1. In this case, the electrons aren't completely transferred, but they move a little closer to the chlorine. If the electrons are a little bit closer to the chlorine and further away from the hydrogen, it makes the chlorine somewhat negative. It's not completely -1 because it hasn't accepted an electron completely, but it's kind of trying to get the electron away from the hydrogen a little bit, so it becomes a partial charge. Its charge exists somewhere between 0 and -1. So it's like a little piece of a charge, but it's not completely negatively charged. So we need to indicate that somehow. We use a symbol to indicate that there's a slight charge by the chlorine, and that symbol looks like this. And I put it up in the corner here, and it's a lowercase delta, which looks like an 8 that doesn't quite get done, and then I put a negative with it. It means just a little bit negative, not completely negative, okay? Just looking at the letters here, right? I write that, and you can see I've already written this from this morning. I write the delta like that. That's the way I do it. If you're to go online and look up Greek alphabet, it would not look anything. It would look hopefully like that. It looks a little bit like a lowercase d, right? And this is the capital delta, right? We've already seen that, right? It means difference. And this is a big D. We're okay with that? We got the big D? All right. Anyway, right? This means the difference. So this means just a little bit of a difference. Get it? It's a little d. So it means it's a little bit of a difference, which means its charge is a little bit negative, a little bit of a difference of a charge. That's really why they use it for that. You might think, oh, that's really funny, Miss Sand. It's a little difference, isn't it? But that's exactly why they do that. So if the electron gets pulled this way, it's not a complete negative charge, but it's a slight negative charge. And that automatically does something to the hydrogen. It's going to become a little bit positive, okay? Now, when you have charges that have moved a little bit like that, and you get something that has a little bit of a negative end and a little bit of a positive end, we call it, whether it's in chemistry or whether it's in physics or whatever, we call this type of a thing that has a slightly negative end and a slightly positive end, we call it a dipole, all right? Because it has two poles. There are lots of polarized things that has two poles. Give me some examples of something else you know that has two poles. Yep. Yeah, magnets, which means I must invoke the fairy princess case of magnets. Right? Magnets have two poles. This is a dipole. This is actually a magnetic dipole, but it is very much like the little dipole that would exist in an HCl molecule. All right? The difference between the dipole on an HCl molecule is that this is an electric dipole. It's made by electric charges moving. This is made by magnets, right? But it's also a dipole. And anything that has two opposite ends, we say is polarized. Therefore, we say that this molecule is polar, because now it has two opposite charges on that particular molecule. Just like the Earth has poles, it's got two opposite ends. Magnets have poles, right? And so this is a polar molecule. This is a polar magnet, right? The difference is magnets have to be polar. You can't have a non-polar magnet. That would be a non-magnet. It just wouldn't be anything. One other way in which we represent the dipole, instead of putting the little deltas, sometimes we use a notation that runs along the bond, and it's essentially a little arrow that points in the direction of the electron's movement because of the delta En. And we put on the end of that little thing a little plus on the tail. So I put a little T on the end, so that's a little plus sign. That tells you that this is the positive end of the molecule, and this is the negative end of the molecule, because the electrons are moving that way. Okay? So that's what a polar bond is. Any molecule or any bond that has a delta En between 0.2 and 1.7 can be represented with these little dipoles. Whether you write it down with the little delta notation or with the arrow, it says the same thing. All right? And technically that little arrow is what we call a vector. And for those of you who have taken physics, you might have learned about vectors. You have velocity vectors and acceleration vectors. This is just a dipole moment vector, we call it. All right? Okay, let's take a look at some example calculations that we can do with this stuff. So which bond is more polar? Which one has the strongest dipole? HCl or HBr? Well, What do I effectively have to do here in order to tell which one's going to have the biggest dipole? What do I have to do in terms of pictures, calculations? What's the simplest thing I have to do? There's one thing I got to do. How am I going to figure out which one has the strongest dipole? What's that, Rachel? Not just the En, but the delta En. Subtract the difference between the ENs. The bigger it is, the more polar it is. It's that simple. So it really is that easy. HCl. We don't need to draw the picture in every case. In this case, it's not saying draw the molecule, put on the dipoles. It's just asking which one's more polar. Delta En, I don't know why I'm using the blue, but it's in my hand. We already know that for HCl. I don't need to see those numbers and calculate it again. What was that number from the last slide? 0.96, I think. That's just the answer without doing the calculation. We did that on the last page. We did it right there. HBr, delta En. What's the H value? I think we know that, don't we? 2.2. Now I need a Br value. And I'm going to get rid of this blue pen. Hardly see the writing. What's the electronegativity for bromine? Yep. 2.96. Let's do the subtraction. Again, I'm not doing that in my head. We crash and burn every time. What's that? 0.76. 0.76. Which one is... Does it work out that way? Yep. What have we got? It's good? Is it good? All right. Which one's more polar? Which one is the strongest dipole? What's that? HCl. Therefore, HCl is more polar. It has the higher delta En. Yep.
Do you have to put a line?
No, you don't. It just means that we ignore the negative. If you didn't put the lines, say you were, right, because you notice we've got 2.2, which is smaller than 2.96. In your calculator, that'll give you a negative 0.76. I'm not concerned about the negative. So if you forget to put the lines and you don't put the negative, I'm not going to penalize you in any way, like if you're doing calculations. It just means don't worry about the negative. Let's do another one. Rank the following from least ionic to most ionic. In this case, ionic is just another term for really polar. So something that's least ionic is something that's not ionic or really far from being polar. Again, what am I doing here to solve this if I want to rank these things in terms of their unequal sharing? And hopefully some of you have already started to do it. What do you got there, Cameron? Yeah, we're calculating the delta En all the way across the line, and then we're just ranking. So go ahead and calculate those delta ENs. You're going to show your work, but I'm going to just write down what you get as answers. But again, essentially, you're figuring out the delta En for all those things. And we've already done HCl, 0.96. On a test, I would look at what the value is of the mark on the thing, right? And then I would determine whether I would want to show my work or not, depending on how many marks I'm going to give. For this particular activity, I'm not that concerned. Excellent. Good question. I forgot. I always forget to address this. In the second part of this lesson, we're going to address how the shape of a molecule affects this polarness, the polarity. But for this lesson, I'm only worried about one bond at a time. So even though I've got something like pH3 and HCO2O and CH4, just compare the delta En of an H to a P. Don't worry about the 3. And you should never multiply it by 3, because what we're learning here is we're determining the polarity of the bond, not of the entire molecule. The second half of this lesson is determining the polarity of the entire molecule. So yeah, for these guys here, just one atom to one atom. And I'll take some numbers as they're coming in. If some people have got, somebody got an HF? If you got an HF, I'll put it up. Carissa, what do you got? 1.78. 1.78. And somebody else with an LIF, if you got it. Yep. 3.0? 3.0. And a pH bond, if you have it. Yep. 0.01. 0.01. H2O, yep. 1.24. And the CH bond in CH3, yep. 0.35. And the CS bond, yep. 0.03. Again, do check across from each other, right? Make sure we haven't made any mistakes. So if I'm going to rank this from least ionic to most ionic, so if I'm starting here, least, what's going first in my list? What's the least ionic thing? Carissa? Yeah, pH 3. So I'm going from, and it's so least ionic, it's almost purely covalent. It's almost 0. So when we say least ionic, we mean equal sharing. So yeah, pH 3. What's next? Somebody just go through it and tell me what comes up next. Carissa, keep going. CS2. Keep going. Is it CH4? CH4. Anybody got another one? Carissa's like losing, she's running out of gas. What do you got? HCl. Next. H2O. I'm moving down here. HF. And LIF. And down over here we've got the most. All right? And if we take a look at that, I'm hoping we're not too surprised. LIF, that's a metal and a non-metal. That's our classic definition of ionic, and it is. Some other interesting things to note. Look at HF. If I were to ask you, what type of compound is hydrogen fluoride? You'd probably say, oh, non-metal, non-metal. Oh, that's a covalent compound because they're two non-metals. But look at how unequal the sharing is. In our bonding continuum, where does that sit? What part of the continuum does that sit in? It sits in an ionic region, which means that's an interesting one. It's so polar, technically according to our bonding continuum definition, HF is an ionic compound. It's just slightly ionic. Can you say that? You can if it's a continuum. Another important one, how would you describe water in terms of its polarity? What adjective could you add to that? Whereabouts in the continuum does it sit? Yeah, Cameron, what do you think? Yeah, it's strongly polar. And that's a very important thing. That strong polarity is what gives water its properties. Water is a very light molecule in terms of mass. It really has no business being a liquid at room temperature. Compared to other molecules of the same mass, they're all gases. But water is so polar that it results in its physical property being a liquid, and that's very important, right? This high polarity is what allows life to really originate, because, you know, life needs water and we need liquid water, and that polarity is a very important thing. All right, that's kind of neat. Now, there's a little bit of homework that goes with this, but I'm not going to let you stop there and work, because I want to now extend polar bonds to the entire molecule. Because sometimes molecules can have polar bonds, but not be a polar molecule. All right? Now, a little heads up before we continue. Tomorrow's lesson is going to talk about how molecules interact with other molecules, and we haven't talked about that yet. And if a molecule is polar, it's very important on how it interacts with other molecules. Because if I have a bond like that HCl bond, which is a dipole, and I bring another dipole close to it, like another HCl molecule, they'll stick together, just like magnets. And when molecules are sticky, that determines their physical properties. If I've got something hard like the lab bench, that simply means the molecules are really stuck together, and I am not going to drive my fist through that lab bench. But if I have something that's liquid, like water, then its molecules are kind of sticky, right? I can move my hand through it, but I can feel it. If I'm trying to run through water, I can get through it, but it takes some effort, you know, when you're playing tag. You know, playing tag in the water. You all do that type of thing, right? You know what I'm talking about. So you can get through the water, but it takes some effort. But if you've got something that is a gas, they're not sticky at all, right? The air around us is made up of non-polar molecules, because when you walk through it, they just get out of the way, all right? So the stickiness of molecules determines their physical state. So we need to continue on and talk about what makes molecules polar, not just the bonds. Okay, so polar molecules. It's a continuation. Would you like it to be a different note? Yeah. All right. We have just learnt the first bullet. The polarity of a bond depends on the delta En. That's what we've just completed. Now we want to determine how to figure out whether an entire molecule is polar. And that's going to depend on two things. It's going to depend on whether the bond is polar, the delta En, and it's also going to depend on the shape of the molecule. This really is why we want to be able to do Lewis structures. A Lewis structure, along with another theory that you'll learn next year called Vesper theory, determines the actual shape of a molecule. Once you know the shape of the molecule and you know if the bonds are polar, you can determine whether the entire molecule is polar. You're not going to learn the overall theory, but I will be able to teach you a simple way by looking at the Lewis diagram to determine whether the molecule is symmetrical or not. And that's good enough information for you for this year. You'll be able to analyze whether a molecule is polar good enough by knowing whether the molecule is symmetrical or not, all right? Next year, we'll do the whole theory and predict the overall shape of the molecule. Now, there's a couple of slides of rules again that we need to do. And what I'm going to do here is I'm going to let you write down what determines a nonpolar molecule. And then we'll do a couple of these examples. And then I'll let you write down what determines a polar molecule. And we'll do an example. And then we will, I'll write down a little bit of a flow chart or one of those concept maps to guide us through this. Because right now this is going to be a lot of blah, blah, blah. So hopefully the concept map will clarify things. Yep. All right. Yeah, you got to go. There'll be some homework associated with this. Catch the end of the movie. You'll see it. Remind your teammates out there they're out to prepare for football. Yep. And that's it. And I don't want to have to leave this room to remind them again. Good luck. So for nonpolarity, all bonds are nonpolar. If there's no dipoles in any of the bonds, then the whole molecule can't be polar. There's nowhere for the polarity to come from. There's no little negatives or positives that can exist. That's easy. The bonds could be polar, but if the molecule is symmetrical, the dipoles will cancel out. Canceling dipoles is kind of a confusing thing. It's not too bad. But I drew the arrow on the HCl, and you can imagine if we've got a symmetrical molecule and all the arrows are pointing in opposite directions, then those arrows would cancel each other away. A left arrow would cancel a right arrow, and an up arrow would cancel a down arrow. It can be done with magnets. If I were to take an elastic band and orient these magnets in such a way that the north and south were right beside each other, what happens is the magnetic field, instead of going out off into space and trying to attract some metal, the magnetic field actually goes around the corner right into the opposite pole. Same thing with on the other end. So the magnetic field becomes encompassed in this very small area, and the magnets essentially cancel each other out. And that's the same with dipoles. You put them really close together in a little molecule, and they'll cancel each other away. Let's do a couple of examples. Yeah? Examples? Yeah, we can do examples. That's fun. Okay. So first let's do, in the first example here, let's do, oh, and they moved my cart. That's great. They did that on purpose because they're football players. pH3. And that's, you know, they're just, that's what they do. They're jocks. And jocks inherently like to pick on geeks like myself. Okay. When you're trying to determine if a molecule is polar or not, first thing you do is draw a Lewis structure, because it's all based on that Lewis structure. So pH3, phosphorus in group 3, 3 bonds, 1 lone pair. This is a nice structure, and because of time and because no one's bringing their pens to their paper, let me show you how to draw this, even though you know how. P, H, 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 lone pair. First thing we need to do is figure out whether any of those bonds are polar. How do I determine if a bond is polar? Yep. Delta En. Delta En, that's all you need to say. Delta En. Delta En equals. We've done a pH bond, haven't we? We could write the numbers down, but I think we've already done it. What is the value? 0.01. As soon as you do that calculation, you can make a therefore statement. Therefore, what's true about those bonds? They're non-polar bonds. Non-polar bonds. And if none of the bonds are polar, which means there are no dipoles in that molecule, what must be true about the whole molecule? It's non-polar. This is the easiest example. If the bonds aren't polar, then you can jump right down to non-polar molecule. If the bonds aren't polar, the molecule isn't polar. Those molecules are not sticky in any way. That would be a gas. Okay? Let's do another example. And what was that example on the bottom slide that they had, or the bottom part where they had CCl4, right? CCl4, I think it was, the bottom one? And that's CCl4, symmetrical molecule example. Down here you should have a CCl4 somewhere. CCl4. CCl4. Again, draw the Lewis diagram. Pencil if you've got a pencil hanging around if you're not sure. Cl. I apologize because the smartboard is so far out of alignment on this end, it isn't even funny. Again, nice structure. I will only have you analyze nice structures when talking about polarity. I don't want you to worry about complex ones. Okay, what's the first thing we do? Delta En. Calculate the delta En. Delta En. Carbon, we've come across, I can't remember the numbers. 2.55 for carbon. 2.55, chlorine, 3.16. I think I remember that one. And what is the En? Or the delta En? Yep. 0.61. 0.61. Where does that sit on my continuum? It sits in the polar region. Remember, it's 0.2 to 1.7. Which means I have to say, therefore, polar bonds. All right. It has the potential to be polar. Now we need to check for symmetry. How do we check for symmetry? I'm looking at the central atom. What does it say at that bottom box? What determines whether it's symmetrical for you guys? This is the easiest way to do it. Yeah, what do you got, Cameron? Right, it has no lone pairs on the central atom. So we check for the bonds, we say therefore polar bonds. Now we check for lone pairs. No lone pairs on central atom. And folks, when you're analyzing these, you can use those short forms if you want. I want you to worry about the logic. I don't want you to worry about the words. And when you can't spell like myself, it causes me stress sometimes when I can't find the words. So, no lone pairs. What does that tell me about the symmetry? If there's no lone pairs, what does it tell me? What's it say in the bottom of that box? Yeah? You're working way too hard. What does it tell me about the symmetry if there's no lone pairs? What does it say at the bottom of the box if there's no lone pairs? What does it say at the bottom? It's symmetrical, contains no lone pairs, which means in terms of symmetry, this is a symmetrical molecule, all right? If there's no lone pairs, it's symmetrical. Here's a model of that molecule right there. Now, it's actually three-dimensional, and it has that tripod shape. We draw it as being flat, but this is a symmetrical molecule. Everything's pointing off, out into space in all different directions. Even if we represent it as a two-dimensional, you can see there's some symmetry there. We should actually write in the dipoles. Which one of my atoms is going to get the little delta plus and which one's going to get the little delta minus? Which atom is going to get the little delta plus of the dipole and which one's going to get the little delta minus? Yep. Yeah, chlorine's going to get the minus. So we should maybe draw them all on there. Delta minus, delta minus, delta minus, delta minus, and on the carbon here, and that's a terrible delta, delta plus. And those guys who messed up my smartboard, I will be cursing them. I've already sent it, Mark, and I'm very busy right now. No, not right now. I got too much to do.
It was here.
Yeah, I sent it down already.
You said no, this, and then fail.
But I sent it down with another student, so it should already be in the office.
No.
Well, I'll have to deal with the office. You'll have to tell them I've sent it because I don't have it.
Is that case we said no?
Yep.
Okay.
There you go.
Thank you.
You're welcome. The molecule is symmetrical, which means all of the dipoles will cancel each other out because they're all pointing in opposite directions. All those little magnets will cancel each other away. And if I have a symmetrical molecule, then I can say that the dipoles cancel, and I can then say, therefore, that this is a non-polar molecule. There's a lot of therefore statements because they all kind of lean on the previous one. Polar bonds, potential for polarity. I check for lone pairs on the central atom. There are no lone pairs. That makes the molecule symmetrical, which means the dipoles cancel away all those opposite pointing charges, which makes the molecule nonpolar. Yes?
Can you explain how you get the charges?
The charges, when I have a delta En, that's between 0.2 and 1.7, I then make the conclusion that it's a polar bond, like in our last lesson. I then go to the En that's the largest, which is the chlorines, and that tells me that the chlorines get the negatives and the carbon gets the positive. Okay? The bigger number gets the negative. Any other questions? Okay, let's take a look at an example of where we can have a polar molecule. On the next slide, I will do the NH3 as an example. And if you want to get started on the NH3, we're going to need a Lewis diagram. You're going to look for the delta En to determine whether the bonds are polar or not. Notice here, this is an AND statement. I need both requirements. I've got to have polar bonds in order to have a polar molecule. With the previous one, if I don't have any polar bonds, then I can stop. The molecule is not polar. So here I have to have polar bonds, but I must have a non-symmetrical situation. I've got to have a lone pair on that central atom, or the atoms aren't all the same. Good to go? So NH3. N, H, H, H. What else do I need to finish my structure? Yeah, Carissa? Lone pair. Excellent. We're looking for polarity, so I need a delta En. H, I believe, is 2.2. 3.04? The nitrogen? Yep. 3.04. So delta En? 0.84. 0.84. Therefore, what can we say about those bonds? They're polar bonds. You need to memorize those numbers on your little chart to determine whether they're polar. It's between 0.2 and 1.7, and therefore they are polar. Whoops, that's not how you spell polar. That's funny. Polar bonds, which means we can put our little charges on it. Which gets what? Where am I putting the negative? Which atom gets the slightly negative charge? Yep, nitrogen. It's the highest. So in this case, delta negative, delta positive, delta positive, delta positive. In reality, this molecule looks like this. Take the top one away, put some lone pairs on it, and you'll notice all of them are pointing down a little bit. That breaks the symmetry. It's not symmetrical anymore. And that's all you need to know at this point. The lone pairs break the symmetry. So, once we've got polar bonds, we observe, yes, and I didn't want that color, lone pairs on central atom. Therefore, what does that tell me about the symmetry? That it's non-symmetrical. Therefore, non-sim. If it's non-symmetrical, those dipoles won't cancel out. I've got one left and one right, but I don't have an up to cancel out the down. So the dipoles do not cancel. And if the dipoles don't cancel, then the whole molecule has some polarity to it. All right? Therefore, if the dipoles do not cancel, then we have a polar molecule. Okay? Now I'm looking at the time. I still want to finish a little flow chart. If I had 10 more minutes, I'd do a few more examples, but that's not going to happen. So here's what you can write down at this point. Just put EG, and I want you to do H2O and CO2, the same analysis that we just did. And you can just make a list and do them, underneath. Do H2O and CO2. And you can also do an NCl3. And I also want you to try a SCH3F. That's a tricky one. You can give it a shot. So what do we got? We got H2O, we got CO2, we got NCl3 and CH3F. There's also some textbook questions. We'll assign those. Don't mind that bottom part. I'm teaching that tomorrow. Textbook questions there. NH3F was the last one. CH3F. CH3F. And there's some homework problems there on the top. Don't mind the bottom. I was away one time, so I assigned it as kind of a reading thing. I'm here tomorrow, so I'll just teach it. But I do want to go back up and do this concept map, because we've got a bunch of little rules, but if we see it out in a nice, map, then hopefully it's better. I know that a lot of textbooks have, make a concept map of World War II or something like that, and everybody makes concept maps, but this is an example of a concept map that I think is functional. So I do want you to write this down. So let's back up to the concept map. Okay? And you can put that, I guess you can put it above the homework, because or right below your homework, you're going to use this. So essentially, we start with some molecule, right? And draw the Lewis. Draw that Lewis diagram. And what's the first thing we do after we draw the Lewis? Delta En. Delta En. However you want to put that on that line or wherever you want to put it. Right? Find the delta En. And then it breaks to left and right. Because if the delta En is between 0 to 0.2, right? If it's between 0 and 0.2, what do we learn about our bonds? Non-polar bonds. Non-polar bonds. And if the bonds aren't polar, I can go straight down to the bottom, because if the bonds aren't polar, what can I say about the molecule? It's a non-polar molecule. If the bonds aren't polar, then the molecule can't be polar. Non-polar molecule. Okay? Make sense? If it's between 0.2 to 1.7, what does that tell me about our bonds? What's the other thing? They're polar. Polar bonds. Polar bonds. After I've determined I've got polar bonds, what do I look at on the central atom? I'm looking for symmetrical. So I'm looking for lone pairs, or if they're non-identical. Let's just talk about the lone pairs for now. So if I'm looking here, I'm looking for lone pairs. If there's no lone pairs, and here I've got yes lone pairs, yes. What happens if there's Oh, that's fabulous. That's great. Thank you. Hannah, you've just ended a fabulous movie-making day. Perfect. Thank you very much. If there's no lone pairs, what do we say about the molecule? If there's no lone pairs to push those bonds around, it's symmetrical. Symmetrical. If it's symmetrical, what happens to the dipoles? They cancel. And then that leads me to there. Dips cancel. Right? So if it's symmetrical, the dipoles cancel, I'm back to my nonpolar molecule. If it is and has lone pairs, what's true? It's non-symmetrical, non-sim, and the dipoles don't cancel, and it leads me to what kind of a molecule? Polar molecule. Polar molecule. And the reason it's polar is the dips do not cancel. And if you follow those steps with those molecules that I gave you for homework, you should be able to determine whether the molecule is polar or not. Each of these little spots are my little therefore statements, right? So every one that you step on or you go to, you've got all those little statements there. That's how you're going to determine whether a molecule is polar or not. And tomorrow, we'll talk about what happens if they are polar or not. Are they sticky? Do they form solids? Or are they not sticky at all? They're non-polar. There's no little magnets there to hold them together. Do they form gases? All right?